Welcome to a beginner's guide to how an oil rig really works. In this video, we'll peel back the layers of the machine beneath the surface, explain the purpose of each subsystem, and show how they interact to drill miles into the earth safely and efficiently. Think of this as a high-level tour that connects geology, machinery, and control systems into a single story. Crude oil forms from ancient organic matter buried under sand and mud over millions of years and then gets trapped by rock layers to create a reservoir. The slide's diagram shows a source rock where oil forms, a porous reservoir rock where it accumulates, and an impermeable cap rock that seals it in. Understanding this geology explains why rigs drill where they do and how reservoirs are found. Reaching those trapped hydrocarbons requires a complex, integrated machine, the drilling rig. While rigs look different offshore or on land, every modern rotary rig is organized around the same 5 systems. In the next sections, we'll break down each system, how it functions, and why their coordinated behavior is more important than any single component. At the heart of a rig are 5 core systems that must work together: power, hoisting, rotary, circulation, and well control. Each system has a distinct role, from generating electricity to managing the drill string, pumping drilling fluid, and preventing blowouts. Later, we'll see how data and automation link these systems into a single, responsive machine under load. The power system is the rig's electrical backbone, typically driven by large diesel prime movers and generators that supply stable power to everything on site. Beyond simple availability, modern rigs use power management systems and uninterruptible supplies to prevent blackouts and manage harmonics. Reliable, high-quality power is the foundation on which automation and sensitive control systems depend. The hoisting system literally lifts and suspends the drill string, using the derrick, drawworks, crown block, and heavy drilling line to manage enormous loads. Traditionally driven by brute force, today's hoisting systems rely on closed-loop control, real-time load measurement, and intelligent automation to reduce shock, manage speed and torque precisely, and keep heavy handling operations safer and more predictable. The rotary system applies torque to the drill string so the bit can cut rock formations, with modern rigs using top drive motors that hang from the hook. Where older rigs used rotary tables and Kellys, today's focus is controlled torque. Automation limits torque, regulates speed, and mitigates stick slip. This continuous feedback between torque and rotation optimizes penetration while protecting downhole tools. The circulation system pumps drilling fluid or mud down the drill string, cools the bit, carries cuttings to the surface, and helps control formation pressure. Pumps, pits, hoses, and solid removal equipment keep the fluid clean and flowing. Modern instrumentation turns circulation into an early warning and diagnostic system by monitoring flow, density, and standpipe pressure to detect well problems before they escalate. Well control is the rig's final safety barrier, designed to stop an uncontrolled release of formation fluids by sealing the well with a blowout preventer stack and associated valves. Accumulators and control logic allow the BOPs to activate rapidly, and modern systems emphasize automated actuation, continuous health monitoring, and redundant control paths, so the system acts instantly and reliably when needed. The drill string is the assembly that connects the surface rig to the bit, made of hollow drill pipe sections, heavier drill collars to apply weight on bit, and a bottom hole assembly with measurement and steering tools. The drill bit itself, whether a tricone or PDC type, cuts the rock, while the pipe transmits rotation, allows mud flow, and guides the well trajectory downhole. Drilling operations happen in coordinated steps. First, you drill ahead, using the power, rotary, and circulation systems to cut rock and remove cuttings. Then you make a connection by lifting and adding pipe sections using the hoisting system. After reaching depth, you run steel casing to protect the hole, and finally you pump cement to seal the annulus while well control stands ready. Each step relies on tight system interaction. Building a well starts on bare land with site preparation and cellar excavation, followed by rig up where the substructure, derrick tanks, and generators are assembled. Drilling and casing deepen the well with concentric pipe strings protecting the borehole, and the project ends with well completion where production, tubing, and the Christmas tree are installed to produce safely. It's a staged construction from dirt to production. What has really changed is that rigs are smarter beneath the surface. Electrification, automation, instrumentation, and systems integration have transformed performance. The five familiar systems remain, but modern rigs depend on how those systems interact under stress, not just how each part performs alone. This shift turns the rig into a system of systems where data and control logic drive safer, more efficient outcomes. A modern rig is a fully integrated, automated machine where safety and performance come from a holistic approach rather than isolated upgrades. Predictable power, correctly tuned control logic, context-aware alarms, and verified system interactions under load are what defines success. In the coming years, the rigs that excel will be those engineered so automation and safety layers work together, not just coexist.